Welcome to the deep dive. Today, we're going underground, really, into the very substance of our planet. Earth is always changing, isn't it? Sometimes spectacularly, like remember Mount Kilauea in Hawaii back in 2018?
Oh, yeah, spewing lava 580 meters high.
Yeah,
Incredible power.
Or tragically, the Turkey-Syria earthquake in early 23. Just devastating figures, 60,000 lives, 1.5 million homeless.
Terrible, and those are the sudden dramatic events.
Exactly. But there are these other changes happening all the time, much slower, so slow you barely notice. And that's our focus today. The quiet story of how rocks are made, how they break down, and how eventually we get soil.
That's right. We're going on a journey basically from the Earth's fiery core right up to this thin, vital layer that supports, well, everything, all life. We'll dig into the types of rocks in the Earth's crust. The lithosphere, litho meaning rock.
Okay.
Then we'll see how they get weathered, broken down. And finally, how soil, arguably the most precious part, actually forms. And, crucially, how we can look after it.
Sounds like a fascinating deep dive. So let's start with the basics. A rock. What is a rock, scientifically speaking?
Good question. It sounds simple, but it's basically a solid, naturally occurring mixture of minerals. Homogeneous, usually.
Right. And the Earth's crust, the lithosphere, is just packed with different kinds?
Tons of them. But we can group them into three main categories based on how they actually formed: igneous, sedimentary, and metamorphic.
Okay, 3 families. Where should we begin?
Let's start with igneous. The name comes from ignis, Latin for fire.
Ah, makes sense.
It really does. These were the first rocks on Earth, formed as the molten planet cooled down billions of years ago. So we often call them primary rocks.
The originals.
The originals. And what's amazing is they're still forming today. You mentioned volcanoes. Well, there are about 500 active ones worldwide, constantly churning out new igneous rock.
Wow, 500. So the planet's still cooking, in a way.
Absolutely. It's a continuous process.
So these igneous rocks, what are their key features? Are they, like, tough?
Very much so. They're the most common type, found everywhere, often in these huge shapeless masses. They tend to be really compact, hard, and non-porous.
Good for building things, then?
Excellent building material, yes. They can look crystalline or even glassy. And there's huge variety, about 700 types based on composition, grain size, texture, color.
700, okay. And you mentioned something interesting. They're often linked with metals.
That's right. Metallic ores are frequently found within or alongside igneous formations. It's a really important connection for resources. Now, there are 2 main ways they form. You get intrusive or plutonic rocks.
Intrusive?
Yeah.
So inside?
Exactly. Formed inside the Earth's crust. Magma cools down very, very slowly under enormous pressure.
And that slow cooling does what?
It allows large mineral crystals to grow. Think of granite. You can often see the different mineral grains quite clearly. Gabbro and diorite are other examples.
Okay, slow cooling, large grains.
Yeah.
Got it.
And specific minerals tend to associate with these, like tungsten, tin, uranium, often go with granite or diorite, while chromium and platinum are more linked with gabbros.
Fascinating. So what's the opposite of intrusive?
That would be extrusive or volcanic rocks. These form when molten lava erupts onto the Earth's surface and cools rapidly.
So fast cooling this time.
Very fast. And because it cools so quickly, the mineral grains don't have time to grow large. They end up very fine grained. Basalt is a classic example, or andesite.
Right. So the speed of cooling makes a huge difference in how they look and what minerals might be there.
Precisely. The formation process dictates so much.
Okay, so we have these primary fireborne rocks. But nature doesn't just leave them alone, does it?
Never. The elements water, wind, ice, even temperature changes. They're constantly working on these rocks, breaking them down into smaller pieces or sediments.
Sediments, okay. And that leads us to the next type.
It does. These sediments get carried away by rivers, wind, ocean currents, and eventually deposited somewhere else, often in layers, maybe at the bottom of a lake or sea.
Layer upon layer.
Exactly. And over long periods, the weight of the overlying layers presses down, compacting these sediments. Minerals dissolved in water can seep through and act like cement, binding the fragments together. And voila, you have sedimentary rocks.
So they're like nature's concrete, made from bits of older rocks.
Kinda, yeah. That's why we call them secondary rocks. They're built from pre-existing materials. And they often have very distinct layers or strata.
Layers, that sounds important.
It is. Sedimentary rocks tend to be softer and more porous than igneous ones, but the layering is key. Because as these layers build up, sometimes the remains of plants and animals get trapped within them.
Ah, fossils.
Exactly, fossils. Sedimentary rocks are our primary source of fossils, giving us incredible snapshots of past life.
Wow. So they're like history books.
They really are. And this raises a crucial point. What else gets trapped in those layers along with fossils?
Let me guess. Based on trapped ancient life. Oil, gas, coal.
Bingo. Fossil fuels. Coal, petroleum, natural gas. These are predominantly found within sedimentary rock formations. The energy that powers much of our world comes from these layered rocks.
That's a mind-blowing connection. Any common examples we might know?
Sure. Sandstone, clay, shale, limestone, these are all very common sedimentary rocks.
Okay, so we have fire-borne igneous and layered sedimentary built from the pieces. What's the third type? What happens if these rocks get sort of cooked or squeezed?
Then you get metamorphic rocks. The name means change of form, and that's exactly what happens.
Change? How?
When existing rocks, either igneous or sedimentary, or even older metamorphic rocks, are subjected to intense heat, intense pressure, or sometimes both deep within the earth, they transform. They metamorphose.
So they don't melt completely, but they change.
Precisely. They don't melt back into magma, but the heat and pressure rearrange their mineral structure, creating a new type of rock with different properties.
So harder, denser.
Generally, yes.
Yeah.
They often become more compact, bulkier, and harder than their parent rocks. The change can be quite dramatic.
Like what? Give me an example.
Okay, think of limestone, which is sedimentary.
Yeah.
Under heat and pressure, it transforms into marble.
Marble.
Or soft coal, another sedimentary rock,
Yeah.
can turn into hard graphite or even diamond under extreme conditions. Clay becomes slate. Sandstone turns into quartzite.
Wow. And igneous rocks can change too.
Absolutely. Granite can metamorphose into gneiss,
Yeah.
pronounced nice. Basalt can become schist.
So it's like extreme rock recycling.
That's a great way to put it.
Yeah.
And like igneous rocks, valuable minerals are often associated with metamorphic processes. Think gold and silver, for instance.
Okay, this is all starting to connect. Igneous forms, breaks down into sediments, forms sedimentary, and then either of those can get changed into metamorphic. Does it go further?
It does. This leads us perfectly to the rock cycle. It's not just a one-way street.
Right, it's a cycle. How does it complete?
Well, imagine that metamorphic rock gets pushed even deeper or subjected to even more heat. Eventually, it can melt.
Back to magma.
Exactly. It melts back into magma. And the whole process can start over again when that magma cools to form new igneous rocks.
So igneous, weathering sediments, sedimentary, heat pressure, metamorphic, melting magma. It's continuous.
It's a constant dynamic process. Rocks are always changing, being reformed, recycled by the earth. It's fundamental to how our planet works.
That's incredible to think about, that slow, constant transformation. Okay, let's zoom in on one part of that cycle, the breaking down part. You called it weathering.
Yes, weathering. It's the process where rocks at the Earth's surface are broken down into smaller pieces. The key thing here is that it's in situ the pieces stay put, at least initially.
Okay, so it's not erosion yet, which involves movement.
Correct. Weathering is the breakdown, erosion is the carrying away. And weathering happens through physical, chemical, and biological means.
Let's start with physical. How does that work? Is it just smashing rocks?
Sometimes, but often it's more subtle. Physical weathering breaks rocks without changing their chemical composition. A big factor is temperature change.
How so?
Well, in places with big daily temperature swings, like deserts or high mountains, rocks expand when they get hot during the day and contract when they cool at night.
Right, that constant expanding and contracting must stress the rock.
Immensely. It causes fatigue, cracks form and grow, and eventually the rock breaks apart. This can happen in different ways. Granular disintegration, where it crumbles. Exfoliation, where outer layers peel off like an onion.
Like an onion, that's a great image.
Or block disintegration, where larger chunks break off. Another really effective physical process, especially where it gets cold, is frost action.
Frost. How does ice break rocks? Seems counterintuitive.
It's clever. Water seeps into small cracks in the rock. When that water freezes, it expands right. Ice takes up about 9% more space than water.
So the ice pushes the crack open.
Exactly. It exerts huge pressure, widening the crack. Repeated freezing and thawing just wedges the rock apart over time.
That's surprisingly powerful.
It really is. And farmers even use this. In cold climates, they plow fields in autumn, let the winter rain and snow saturate the soil, and the frost action helps break up compacted soil clods, making it easier to work in spring.
Using geology for farming. Okay, so that's physical force. What about chemical weathering?
Chemical weathering involves chemical reactions changing the minerals within the rock, making it weaker. Air and water are key ingredients here.
Like rust.
Precisely. Oxidation is a perfect example. Iron minerals in rocks react with oxygen, usually in the presence of water, to form iron oxides rust. That reddish-brown layer weakens the rock.
Makes sense. What else?
Carbonation. Carbon dioxide from the air dissolves in rainwater, forming a weak acid called carbonic acid.
Okay.
This acid is surprisingly good at dissolving certain rocks,
Yeah.
especially limestone and marble. It can carve out cavities, caves, even cause sinkholes over long periods.
Wow. So acid rain, essentially, but natural.
Sort of, yes, a very mild natural acidity. Then there's hydration, where minerals absorb water, causing them to swell and stress the rock. Feldspar changing into kaolin clay is an example. And solution, where rainwater simply dissolves soluble minerals like rock salt or gypsum directly out of the rock.
So rocks can literally dissolve away.
Parts of them can, yes.
And the third type was biological, living things.
Right. Biological weathering. This involves plants, animals, and us humans. Plant roots are surprisingly strong. They grow into cracks, seeking water and nutrients, and as they thicken, they wedge the rock apart.
I've seen that on pavements.
Exactly. Burrowing animals too, earthworms, rabbits, ants they dig, loosen soil, expose fresh rock surfaces to other forms of weathering.
And humans. We're probably quite good at this one.
Unfortunately, yes. Quarrying, mining, building roads, even farming, all these activities break up rock, remove protective vegetation, or expose rock faces, speeding up weathering significantly.
Okay, so rocks are constantly breaking down. What happens to all those broken pieces, especially on slopes? You said weathering is static, but the pieces must move eventually.
They do. And that movement, driven primarily by gravity, is called mass movement or mass wasting. It's when weathered material moves downslope.
Like a landslide.
A landslide is a dramatic example, yes.
Yeah.
The sudden, rapid movement of a large mass of rock and soil down a steep slope. Very dangerous, especially in mountainous areas during rainy seasons.
I remember you mentioning a specific example in India.
Yes, the Nasrikad landslides on the Jammu-Srinagar highway. They used to block the road for maybe 40 days a year on average. It was a huge problem.
40 days, wow.
Until they built the Dr. Syama Prasad Mukherjee Tunnel. It's India's longest road tunnel, 9.28 kilometers, which bypasses that whole landslide-prone section, cut the distance by 30 kilometers and travel time by about 2 hours. Shows the impact these movements have.
Definitely. Are there other types of mass movement besides landslides?
Sure. You have things like earth flow, which is slower movement of water-saturated clay and silt, and mud flow, which is faster, like a river of wet rock debris, often channeled down valleys.
So all this material moving downhill, what's the bigger picture? What does it contribute?
Well, as this mass of broken rock moves, especially when carried by rivers, there's constant grinding. Rocks bump and scrape against each other.
Breaking down even further.
Exactly. It creates smaller boulders, gravel, sand. The very materials we rely on for construction. Concrete, roads, building foundations. Much of the raw material originates from rocks broken down by weathering and then transported and further ground down by mass movement and erosion.
It really is all connected, from a mountain breaking down to the house we live in.
Fundamentally, yes.
So this journey of breakdown and movement eventually leads to the finest particles, right? Which brings us to soil.
The ultimate product in many ways, soil.
Yeah.
That uppermost layer of the Earth's crust, made of fine rock particles mixed with organic matter or humus.
And it sounds simple, but you called it the most precious part. Why so crucial?
Because everything depends on it, agriculturally speaking. Our food cereals, fruits, vegetables. Our clothing cotton, wool, animals eat plants grown on soil. Our shelter timber, even bricks made from clay soil.
Wow, okay. Pretty much everything.
Directly or indirectly, yes. Even industries like pottery rely on specific soil types. It underpins civilization.
So let's look closer at this precious layer. If we could see a cross-section, what would it look like? You mentioned a profile.
Yes, the soil profile. It shows the different layers or horizons that develop over time. It's like reading the soil's history.
Horizons, okay. What are they?
At the very top, you often have the O horizon, O for organic. This is a dark layer, rich in humus, which is decomposed plant and animal material, full of nutrients.
The good stuff for plants.
Absolutely.
Yeah.
Below that is the A horizon, or topsoil. This is a mix of mineral particles, sand, silt, clay, and humus. Most plant roots live here. It's the layer farmers cultivate.
Right, the vital layer.
Then comes the B horizon, or subsoil. It's usually lighter in color, has less humus, more clay perhaps. Rainwater can leach minerals down into this layer.
Okay, what's below that?
The C horizon. This is partly weathered, parent material chunks of rock that are clearly breaking down but aren't soil yet. It sits on top of the bedrock.
And the bedrock is?
The R horizon, R for rock. This is the solid, unweathered parent rock from which the soil above ultimately derived.
Oh, A, B, C, R. Got it. It's a whole layered system. But how does it even form? You said it's precious, implying it's not easy to make.
Not easy and incredibly slow. It can take hundreds, even thousands of years to form just 2 or 3 centimeters of topsoil.
Thousands of years for 1 inch.
Right.
Wow.
It really puts soil loss into perspective. Several factors control how quickly and what kind of soil forms.
Like what?
Well, the parent rock itself is key. What minerals does it contain? How easily does it break down? Sandstone tends to make sandy soil. Shale makes clayey soil.
Makes sense. The starting material matters.
Definitely. Then climate. Temperature and rainfall are huge. Warm, wet conditions generally speed up weathering and biological activity, so soil forms faster than in cold, dry places.
Okay, rock type and climate.
What else? Relief, or the slope of the land. On steep slopes, weathered material gets washed or slides away quickly, so soil struggles to develop. Flatter areas allow material to accumulate, leading to thicker soils.
Gravity working against soil formation on hillsides.
Exactly. And finally, time. It just takes a very, very long time for all these processes to work and create a deep, mature soil profile. Older landscapes generally have thicker soils, assuming they haven't been eroded.
So it's a slow recipe with rock, climate, slope, and time as the main ingredients. What makes the perfect soil, ideally, for growing things?
The ideal soil. You're looking for a good balance. Roughly 45% mineral particles, providing the structure and nutrients like NPK, nitrogen, phosphorus, potassium.
NPK, right.
About 5% organic matter, or humus, which holds water and nutrients and improves structure. And then, crucially, about 25% airspace and 25% water space within the pores.
Air and water. Equally important.
Absolutely. Plant roots need both. And the texture matters, too. Loam is often considered ideal. It's a mix of roughly 40% sand, 40% silt, and 20% clay. Good drainage, but also holds moisture and nutrients well. Even the pH matters slightly acidic. Around 6.5 is often best.
There's a whole science to it.
There is. It's called pedology, the study of soils.
Pedology, okay. So we have this incredibly complex, slow-forming, vital resource. But you hinted it's vulnerable. How?
Through soil erosion. This is the removal of that precious topsoil, the O and A horizons, mainly by wind and running water.
Washing or blowing away the good stuff.
Exactly. It reduces the soil's thickness, strips away nutrients, and lowers its ability to support plants. It's a massive environmental problem globally.
How does it happen? Are there different kinds?
2 main types are usually discussed. Sheet erosion is when rain or runoff removes a thin, fairly uniform layer of soil from the surface, almost like peeling off a sheet. It can be quite insidious because it's not always obvious at first.
Sneaky erosion.
Very. Especially damaging if there's no plant cover to protect the soil. Then there's gully erosion, which is much more dramatic.
Gullies, like deep channels.
Yes. On uneven land, concentrated runoff carves out small channels. Over time, these get deeper and wider, turning into gullies, then ravines. It can carve up farmland, making it unusable. We mentioned the Chambal Valley in India. That's a classic example of severe gully erosion creating badlands.
So what drives this erosion? Is it just rain and wind?
Those are the physical agents, yes. Heavy rain, strong winds, steep slopes all contribute. But often, human activities make it much, much worse. These are the avoidable factors.
Avoidable? Like what?
Overgrazing is a big one. Too many animals stripping the land bare of vegetation leaves the soil exposed. Deforestation, cutting down trees, removes the root network that binds soil and the canopy that protects it from rain impact.
Right, losing the natural protection.
Exactly. Also, mining disturbs vast areas. Over-irrigation can lead to waterlogging and salinity, damaging soil structure. Excessive use of chemical fertilizers can degrade soil health over time. Even things like brick making, which removes topsoil, or unscientific farming methods that don't protect the soil, contribute significantly.
It sounds like we're often our own worst enemy when it comes to soil.
In many cases, yes. We need the resources soil provides, but sometimes our methods of extraction or cultivation accelerate its loss.
Which brings us to the crucial question. How do we stop this? How do we protect the soil? Soil conservation.
Yes, soil conservation is about protecting soil from both erosion and exhaustion, that loss of fertility from overuse or poor management. And there are many effective strategies.
Let's hear them. What's number one?
Afforestation, planting trees. It's fundamental. Tree roots bind soil, leaves reduce raindrop impact, and forests improve the whole water cycle. Slogans like, each one, plant one, teach one, capture the spirit. India's Van Mahotsav Festival promotes tree planting every July.
Planting trees seems like a win-win.
It really is. Remember indoor planting 1.1 million saplings in a day? That's the kind of effort needed. India aims to get its forest cover up from around 24.6% to 33%.
Ambitious, but necessary. What else?
Controlling overgrazing. Managing livestock numbers prevents stripping vegetation. Growing specific fodder crops can provide feed without degrading pastures.
Okay. What about wind erosion?
Shelter belts. Planting rows of trees or shrubs perpendicular to the prevailing wind direction slows the wind down near the ground, protecting fields. They're planting huge belts around Delhi and in Rajasthan.
Smart. Using nature to fight nature, in a way.
Exactly. And then there are specific farming techniques. Terrace farming on hillsides, cutting slopes into flat steps, slows down runoff dramatically.
Like giant stairs on the mountain.
Pretty much. Contour plowing means plowing along the contours of the land, not up and down the slope. The furrows act like little dams, trapping water.
Simple but effective.
Very. Strip cropping involves planting different crops in alternating narrow strips along contours. If one crop is harvested, the other still protects the soil. Crop rotation is key for fertility. Planting different crops in sequence replenishes nutrients that others deplete. Legumes, for example, fix nitrogen.
So it's not just about stopping erosion, but keeping the soil healthy, too.
Absolutely. Bunding fields, building small earthen walls around the edges holds rainwater in, preventing runoff and erosion. On a larger scale, building dams and check dams controls river flow, reduces flood intensity, and traps sediment. And sometimes, the best thing is to give the land a rest, leaving it fallow for a season, allows natural processes to restore some fertility.
That's a really comprehensive toolkit. It feels like there's a lot we can do.
There is. It requires knowledge, planning, and commitment, from individual farmers to governments.
And speaking of commitment, there's that incredible story from India you mentioned earlier, the Chipko movement. Tell us about that.
Chipko. A truly inspiring example of grassroots conservation. It started around 1973 in Uttarakhand, in the Himalayas. Logging companies were moving in to cut down forests that local communities depended on.
So the people fought back.
They did, in a remarkable, non-violent way, led initially by Chandi Prasad Bhatt and famously involving village women like Gaura Devi. When the loggers came, the villagers literally went and hugged the trees. Chipko means to embrace or to cling to.
They physically shielded the trees.
Yes, sometimes staying there all day and night, putting their bodies between the axes and the trees. Their slogan was powerful. What do the forests bear? Soil, water, and pure air. It connected the trees directly to their survival.
Wow. That takes incredible courage.
It does. The environmentalist Sunderlal Bahuguna helped spread the movement's philosophy. Its success, using Gandhian nonviolent principles, eventually forced the government to listen. In 1980, Prime Minister Indira Gandhi enacted a 15-year ban on commercial logging in those Himalayan forests.
A huge victory for local people and the environment.
A landmark moment. And incredibly, the spirit resurfaced in Delhi in 2018 when citizens protested against large-scale tree felling for development projects using similar hugging tactics. The legacy endures.
That's a powerful reminder of what collective action can achieve. So wrapping this up, we've traveled an immense journey today. From the Earth's fiery birth creating igneous rocks,
to the slow, patient work of weathering, breaking them down.
the layering of sediments forming new rocks and trapping history.
The intense transformation creating metamorphic rocks.
All part of the endless rock cycle and culminating in that thin, vital layer of soil.
Formed over millennia, supporting all life, yet so vulnerable to erosion.
And finally, the crucial human efforts, inspired by movements like Chipko, to conserve this precious resource through smart farming, afforestation, and community action.
You know, it really strikes me how these slow, almost invisible processes, rock formation, soil building, are just as powerful, just as fundamentally shaping our world as the dramatic earthquakes and volcanoes, maybe even more so in the long run.
That's a great point. It raises a question for you listening. What aspect of the slow geological dance stood out most to you? Does understanding the journey from rock to soil change how you see the ground you walk on? The Earth is always changing, subtly or suddenly. Thinking about the immense power of these gradual processes, how might that influence our own actions, our relationship with the planet day by day? Something to think about.